recording. Good job. And the product rule and quotient rule. Product rule, you cannot just differentiate each piece and be done with this. Unfortunately, you have to use the formula derivative times copy plus copy times derivative. Quotient rule is derivative of the quotient, square denominator, differentiate the top, copy the bottom, minus, that's important, copy the top derivative of the bottom. If you missed this class and you did not do any homework right now, it will be surprising to you. But luckily, we're going to do more examples right now, so it should be a little bit better. Let's practice a little bit more and jump into chain rule. So, if h of x is given as 8 sine x times cosine x, what is h prime of x?
We're just using h in this case to mean a function,
Yeah.
not h to mean h.
H is a function.
H to mean small c.
Yeah. Good question.
Sorry, sometimes.
No, it's a good point. H reserved for small change. Delta x is also reserved. You will see I, J, K will be used. But at some point, you can name function anything you like. So first letter of your name, C of x, why not? I like J of x. But the weirdest one I saw, one professor named the function O of x. And it was in graduate school, and I told him, really? Oh, that looks horrible. And then since then, he did not like me. So I probably should not have said it. It's like a bad Russian straightforwardness. Anyway, but it is weird. Who uses O as a name of the function? So you see product. Either you see it like so, and you factor out 8. Or usually students see it like so, 8 sine times cosine, u times v. Reminding you, until you memorize it, you have to remind yourself, u times v prime is derivative, not derivative, plus not derivative, derivative, at any order you like. I like starting with u, and this is how it looks like, u prime v plus u v prime. If you use f and g like I use in the note in the book, same thing. If you use f of x and g of x, same thing. I just like u v because it's short. Doesn't matter. It's just how to mnemonically you can memorize it. Let's do it together. I can call someone if you want to come here and do it for everyone. But if you don't, let's just do it together. What is u prime? Derivative of 8 sine is? 8 cosine. All agree, disagree?
Yes, right.
Good job. Now what do we do? Copy v. V is cosine. So I'm just copying it. Don't touch it. Plus sine. Copy u. U is 8 sine x times derivative of v. I'm locating v. Oh, maybe I should do it visually like so. V is cosine. Derivative of cosine minus sine. Remember that. Kinda that's all.
Cosine squared x.
If you want to simplify it, you're right. It's going to be 8 cosine squared minus 8 sine squared x. And you can factor out 8 if you want. It's good like that. So my main goal is you know how to differentiate.
Doesn't that equal to 1?
A good question. Cosine squared plus sine squared is 1. So if that would be both minus, we would factor out minus, and it would be 1. Very good catch that you noticed that. But not just minus. How do you feel about this? Try to wake up and, because doing it together is nice, and then you go home and you do it like thousands of times at home. And it's just inevitable that you have to do so many different things, and so different fractions, and again and again and again. 2. Let's do quotient rule, and let's call it, what name do you want to call it? N. Why not? N of t. And it's going to be square root of t plus 4 over square root of t minus 1. This is the quotient. Quotient means fraction. That's the quotient rule. N prime of t. Prime means derivative. The same notation you can write down dn over dt. That is the same thing, just for you to know. Means derivative of n with respect to t. So it's u over v. That's u. Reminding you, derivative of the quotient rule is start with squaring the denominator. So that's what I'm going to do. I'm just going to square the denominator and forget about it. Usually we do not do anything about that. It's just squared. It looks good. The numerator almost follows the product rule, but with negative sign. Start with differentiating the top. So u prime, order now matters. Then copy minus copy derivative of the bottom. So derivative of the top times copy denominator minus copy the top times derivative of the denominator. Now that is going to be a hard part. So denominator was easy. The numerator will be interesting. What is a derivative of the square root of t plus 4? 1 over 2 square root of t. That was amazing and difficult. So let me make a note. How do we know that? Always take a pencil and work it out to check that you did not make a mistake. Square root of t prime is t to the 1/2 prime. That is called power rule. 1/2 goes down. T raised to the 1/2 minus 1. That is negative 1/2. You can keep it like this, or you can rewrite it as 1 over. 2 is in the denominator, so I will keep it there. And t can be written as 1/2 in the denominator, or a square root. You don't have to memorize this, you just know the power rule. But some people memorize it, and that makes it faster on the test, for example. So, which way would you like me to keep? This way or this way, with the minus 1/2 or with the square root? Surprisingly, you chose square root. That's good. Mostly students don't like it for some reason. Good job. But what happened with plus 4? Plus 0, right? Derivative of plus 4. 4 is isolated constant. Derivative of the isolated constant is 0. Versus if it's here, then it stays. So remember the difference. If constant is multiplied, you keep it. If you add or subtract, it gives you 0. We don't write 0, so I just close it. This is u prime. Now, copy v. So I'm just gonna copy v. I need to locate what is my v. V is the denominator. So I'm just copying it. That is my v. Negative sign is important. Part of the formula. Copy u. U is the top. Stop moving. This is numerator. Square root of t plus 4. Times, so that is u. Finally times v prime. I'm following the formula. V prime in black. V is square root of t minus 1. And you can use the same result we had before. 1 over 2 square root of t minus 0. If you simplify all of this, it will give you some kind of nice answer. Which is, there's a lot of distribution happening, factoring out. Too annoying to go through this. So I personally like it like this. This means you know the formula and you understand how to use it. Simplification is needed for the multiple choice part of the exam. Other than that, it's fine. This is good. Questions? What do you think? Hard, easy, horrible, not too bad. Let's do one more. 3. So let's do 3 secant x minus e, let's do 4.1 e to the x plus 21. Oh, and we should do some 21 plus cosine x multiplied by x cube. Okay, that's very nice. Why not? Let's call it somehow. What letter do you like?
Q.
Q, why not? Let's do Q. Q of x is this Q. Good, very good choice. Let's take derivative of Q. Let's do it slowly. What is derivative of 3 secant x?
3 secant x.
3 secant x. Remember, secant likes itself, so it copies itself. And then, since it's connected to tangent, it includes the tangent x.
Does the 3 not get copied?
So I wanted to say it. Good job for asking. 3 is multiplied. If a constant is multiplied, it's like a sticker. It should stay. If the constant is added, like this one, that one give you 0. Make sense? Because if it's multiplied, it's your rate. A rate should stay. Minus. We did mention derivative of e to the x and log. Who remembers what it is?
Yes.
E to the x is a pretty cool, unique case that if you ask how fast e to the x is, the answer is e to the x fast. Because exponential growth is one of the fastest growths in the universe. That's why the rocket goes to the space with exponential growth. The cancer division is having exponential growth, and so on. Yeah.
If it was b to the power of 2x.
We're going to do it today, actually. Don't spoiler. Good job. That's chain rule. Chain rule. So what is going to be minus 4.1 e to the x? What is it going to be?
Minus
4.1 e to the x.
E to the x. Is this weird to you that it stayed the same or not?
Not at all.
I will tell you a joke after we finish this about e to the x. Plus 21 gives you
0.
Good job. Now cosine x times x cubed gives you what?
3x squared.
This is product rule. So be careful on the exam. You might want to make a mistake and just do it minus sine x times 3x squared. That is not good. You cannot just put derivative on each. That's why you have a product rule. Product rule should be applied. So I will do plus, and I will open parentheses to indicate the product rule. Maybe I will even change the color, like so. Derivative of u is minus sine x. That's derivative of cosine. Multiply by copying v. That is x cubed. Make sense? Copying. Plus copy u, that is cosine x, times derivative of x cubed is 3x squared. We're done. Does it make sense? This is my product rule. U prime v plus u v prime. So anytime you see a function multiplied by a function, you do product rule. Every time you see a constant multiplied by a function, that is not a product rule. Yes.
I'm confused on how u and v was chosen.
Yeah, that's a very good question. Like, how do we choose u and v? I just look at the product and put in my mind parentheses like so. That's how I choose it. And then whatever is in the first parenthesis, I call it u, and the other one is v. Kinda, that's all I can say. What do you think? Does that make sense? So, like, let me see. If you have secant x times e to the x times tangent x, that is also product but twice. Then I'll have to decide how to choose u and v. Parentheses will be 3 of them. Then I will be doing, for example, u, and this will be v. Or, bless you, I can redo it as u, and this will be v. So I would say it's not a unique way how you can choose your u times v. But since you call it a product rule, you try to identify what are the factors in front of you, and one should be chosen as u, and the other one should be chosen as v. You can also see it as f of x times g of x. 2 or more functions are multiplied. When you differentiate a product, you have to do product derivative of the first one, copy the second one, plus copy the first one, derivative of the second one. A little bit better? Yeah, keep asking. It's not supposed to click at some point. Yes.
In the problem above, Is there a reason why the first part where the Fuji is beginning like that? Why that wasn't used?
It's very clear. You can do that. I can see so many ways to do it. Secant and e to the x first time, e to the x tangent second one, or maybe even x. It's creative, yeah. Yeah. Because product can be flipped, then means your choice can be flipped.
Every time you're doing the secant.
So,
Okay.
that were nice questions. Good job, people. That is just example of the choice. Choose U and V. Math will figure it out. The moment you fix U and V, math will work. That's a good part of it. Yeah.
So if we do that, if we find this in the test, we do the multiplication rule with n multiplication.
Yeah. It will be product inside of the program. We don't give you that in the test. That's weird choice. So a funny joke about e to the x before we move on. Very nice, very old Soviet anecdote to remember derivative of e to the x. My advisor told it to me, and his advisor told it to my advisor. He's just on time for the Russian joke. So it's a very old Soviet joke, very interesting. In the math house where the math people are, there are two mathematicians. And first of all, it's already funny that it's not surprising that there are two mathematicians in the math house. So that's kind of the funny part of the joke. And then one is aggressive, and one mathematician is running around the math house and yelling at people, I'm going to differentiate you. I'm going to differentiate you. Nobody knows what it means, so they are very afraid, and they run away and hide. The doctor walks around to see what's going on, and he sees that one patient did not care. He approached that patient and asked him, how come you're not afraid? He will differentiate you. And that patient, which happened to be a second mathematician, would say, I don't care, I'm e to the x. Haha, yeah, I know, right? But it's a cool joke to remember that e to the x prime gives you e to the x. And soon we're going to go into integration, and it will be the same thing. The integral of e to the x is also e to the x. Because that's how fast the function is. The speed of the function matches with the function. I think the funniest part of the joke is about having crazy mathematicians in the math house, which is partially is not made up. Before my generation, in math department of my Ukrainian university, we were the only one who had our own psychologist on the floor. None of other majors had a psychologist. We had. So think about that. Then the psychologist was eliminated, but before that, we had some. So that's kind of interesting. Chain rule, 1.7, I think, yeah. Chain rule has so many cool applications in calculus 1, 2, 3, machine learning. It's pretty fascinating. Chain rule actually is very interesting. Chain rule is used in computer science, in engineering, in biology. Everything you can imagine has chain rule. And because of that, chain rule is hard to learn. So most of you will be challenged to learn chain rule, to master chain rule. So chain rule is the idea of how would we take a derivative. So we learn how to take a derivative of 3x squared plus x, just an example. That is 6x plus 1. But how will we take it if it's cubed? That is a question. From one point of view, you could break it into three products, 3x squared plus x, 3x squared plus x, and 3x plus x, and then you do product rule. However, what we're going to teach you is nesting of functions. Not nasty, nesting. Function inside of the function inside of the function. This is a function, let's call it u, that was cubed. So there's a function happening inside of the function. And that's exactly what biological processes do. When your heart beats, that's one function, but inside of the heart there is a blood flow. That's another function inside of the function, and the rate of the blood flow has also its own function. So the more complicated organism is, the more chain rule it involves. And that's why chain rule zooms into a function to see how the initial change, which is input, can affect the final result. How the small change of the blood flow in your heart might change the heartbeat. That is exactly a good example of the nesting functions. Function inside of the function inside of the function. Bless you. So, one of the coolest applications I always show is how chain rule, okay, that should be rule. How chain rule is used by AI, artificial intelligence, for image recognition. That's why I'm doing the honor project about this as well, because it's pretty cool. So this is what I showed you at the beginning. I'll give you some interesting information about what is artificial intelligence does. That's image recognition. So your smartphone can recognize your face. And now if you have Google Photos, it can search now flowers, and it will give you photos with flowers. Sometimes I just want to search my nail art from previous years, and I just type it and gives you my nail art. So how does it do that? It's actually not a very simple task to teach, say, a blind person what is different between a dog and a cat. They have so many in common. Full legs, furry, cute, small, big sizes, they all like that. So how would you teach? How would you teach a robot what is different? So what you do is you feed as many images of dogs as possible, millions and millions of dog images into the system, and then on every step, the computer will give you a prediction. I think it's a dog because it has a tail and 4 legs, so I'm not sure, let's say 55% accuracy. Next step. If it's wrong, you give it a punishment. If it's right, you move to the next step. Next step, it says, okay, so it has 2 ears. Now I'm close to 65% that it is a dog. Next one. On every single step, the computer does prediction, and the final, you hope it will tell you it's dog. That's actually a hope. It will tell you, I think it's dog with 98% accuracy. And every step requires chain rule. That is a pretty cool idea. Every step takes chain rule, because every time it makes a mistake, it's a function inside of the function. All those situations it has to consider, the eyes, the nose, the fur, all of this will be fed into the computer. So all this hidden part, all those arrows you see, those are chain rules. Pretty cool. Question for you. I was reading the article. What do you think was the first animal that computer learned really fast? Think about it, it's probably not very different from each other. So one species of animals doesn't move too much, doesn't have that face expression. Humans definitely are the hardest one because we're too different, we smile and so on. So what do you think it is? The easiest one. Elephants, someone told me a pretty interesting idea.
They are extremely distinct, so it's all any animal species at
It's
all?
like some kind of type of animal. Computer, what it says, instead of 1 year learning about the dog, it got it in 3 minutes.
Starfish.
What is it?
Starfish.
Starfish looks like a bomb. I don't know, but a good point. But
Well,
it looks like a
don't-
plant.
I'm assuming they were only being fed data from animals.
Yeah, I don't know about that.
Turtle.
Turtle, interesting idea, but they are big and small.
And turtles are surprisingly actually faster than people think.
And they might hide, so how would you explain that this is on the rock? Right? More ideas? Creative ideas? Cockroach? What is a cockroach?
Cockroach. One of those beetle.
But there's so many insects. It's kind of hard to explain the difference, even to like a child. Right?
Yeah, cockroaches.
Snakes, very popular opinion. But snakes looks like a rope also.
And
There's so many fishes. Are you kidding me? Yes?
A horse.
A horse. There's so many kind of species with 4 legs and.
needed motion.
But good idea. Motion's also different. And colors. Giraffe's a good idea because it's pretty unique. A penguin. So interesting. Not only all penguins are black and white. They're more or less the same size. And when they walk, they always have like this one position. So it's not like they're gonna just jump or do something weird. They always look like this. So it's pretty cool. Yeah, they do. But it's pretty cool that the penguins were the first one to teach. And then other animals show up. That's kind of pretty cool idea here.
So like giraffes, there's less variation between species than with penguins.
I like the giraffe idea. I like the giraffe idea, definitely, yeah. It is smart because it's a unique animal after all. So, what I wanted to say is, oh, I forgot this. So, the way I explain channel is using Russian dolls, which makes sense. Surprisingly, it was not my idea. An American friend told me, you probably teach channel with Russian dolls. And I'm like, really? Oh, okay. And since then, I started doing that. So, since it is, should I upload it or not? since it is, I lost my file, but okay. A function inside of the function inside of the function. It's exactly what Chris.
Sorry.
It's exactly what Russian doll is, which matryoshka, by the way. So you have a function outside, you differentiate this function. Open it, only then you're allowed to open it. Then there's a function inside. Now you can differentiate it. And the trick is you cannot differentiate the next one until you finish differentiating the previous one because you don't see it. Then the next. Then the next one, and so on. So that is interesting that it's exactly, American instructors teach it using onions. I teach it in Russian dolls. Yes.
What is the meaning behind like the Russian doll having like all this separate? Like,
Yeah, I will show you right now in a second. So by the way, Russians and Ukrainians, we don't own Russian dolls. Nobody owns Russian dolls. They still exist only for one reason. For tourists like you. So tourists come to Belarus, Poland, and Russia, and they buy the Russian dolls. That's why we still make them. But none of us ever played with them. We don't even know why they exist. They exist like a long time
They're
ago.
pretty though.
So this one was a present from Salt Lake City, an antique store from my American friend. And this one is like 35. So the idea of the chain rule is, that's exactly what you asked, like how does it connect it to what I just said. There is a function f of x, and then it's inside, so I'll make a space. I probably put it inside like so. F of x is inside of g, so g of f of x. And now maybe g is inside of, I don't know, m. So now it's m of g of f of x. Think about that. And so on. The more you do, the more nesting it does. Nesting. Right? Or like onions. You need to unfold these. You need to keep unfolding them to figure out what to do. So differentiation works like this. You always go from outside to inside. And it's easier just to show you on the example, which we already had here. 3x squared plus x cubed. If a function, say h of x, is 3x squared plus x cubed, your first goal is to identify which function is inside and which function is outside. So which one is the inner function and which one is the outer function, right? Outside function. Okay, what do you think is inside and what do you think is outside?
Outside is the 3 cube.
Cube, yeah? And what's inside?
3x squared plus x.
3x squared plus x. In this case, it's visually. One thing is inside, this guy. This function is inner. This function, which I cannot name it yet, that's exactly the idea of the Russian dolls. Until you open the outside one, you don't know what's inside. Yeah, you do see it's 3x plus x, but you have to imagine that you don't know it yet. What you see is this function, let's call it u, is u cubed. That's what you see. So there's some kind of function cubed. So what you see is a polynomial, and what we're gonna do, we're gonna use power rule, because that's what we do with powers. H prime is 3 goes down, copy whatever was inside, decrease the power. Does this make sense? This is not the end though, this is not the end. So the inner function, I'll put it inside in green, 3x squared plus x. You copy, and this is the most confusing part for students. We don't differentiate the function inside until we finish differentiating the function outside. This is exactly the idea of Russian dolls. Now I'm opening the Russian doll, and I see 3x squared plus x inside. Chain rule is about product, so this is where chain rule actually happens. Chain rule, it's a chain. The chain reaction tells me, look inside, what do you see? I see 3x squared plus x. Differentiate that and multiply the result. 6x plus 1. And we are done. What do you think about that?
Oh,
That is the answer.
why are we multiplying by 6? Wait, why are we multiplying by 6?
Derivative of 3x squared plus x.
What is
So it is u prime, where u is 3x squared plus x,
Oh, because,
right?
because of the product rule.
Yeah. It's not the product rule, it's power rule here.
But I'm confused as to why it's not just, why we didn't just differentiate the thing inside it, why we multiplied by it.
Yeah, multiplying, that's a good question. So let me explain one more time. Differentiating the outside function, differentiating the inside function, multiplying because it's and. If you ever took a class where they explain logic, and is a product. So derivative and derivative inside. Derivative of the function outside at the inside function. And derivative of the function inside. And is a product.
Is there a numerical version of the chain rule?
Numerical version, just with numbers?
Yeah, I mean, it's like, there's an algebraic version of the chain rule.
No, it's functions. It's about functions, yeah.
Oh, sorry.
Yeah, functions. So this is the matryoshka. Let's do one more. Who can help me with this one? Which function do you think is inside and which function do you think is outside?
15 is outside.
This one is inside. It's inner. Let's call it u. U is a very popular thing to call something inside. We call it u substitution sometimes. So it is u to the 15. How do we work out u to the 15? It's 15u to the 14, right? So 15 goes down, u to the 14. But instead of writing u, which many instructors teach you to do step by step, write down u and then you substitute it back. That's too slow. Just remember, derivative of the function outside at copied function inside. So you cannot touch it until you're done differentiating the function inside. Does it make sense? It's a pure rational idea. You don't see this guy inside until you finish differentiating the previous step. So that's why it's called chain rule. It's a chain reaction. When you finished, now you can put a product and it unlocks your possibility to see what is actually u. Because before that, it was something to the 15. That is 15 something to the 14 times. Derivative of that something is, oh, it's actually 3x to the 7 plus x, which is plus 1. Amazing. So, done. So you see, copy, differentiated. This is the answer. No simplification needed, no need to distribute, nothing. Yes?
If the one exponent was like a 2, what would you do for on the very outside?
If one will be inside,
If the exponent, like the one, that's like, oh, that's fine.
oh, it's prime. Yes, thank you for pointing this out. Let's not mix this up. This is derivative. Yeah, that's derivative sign. So I keep using it all the time because it's easier. This is this prime. Derivative. Let me use a different one, then maybe you'll get used to different. This is the same thing as saying d of cosine of 3x cubed over dx. This is what you will see in the literature, but I like prime because it's easier to write. So it's not 1, it's prime. Okay, this one. Which function is inside and which function is outside?
The x cubed is inside, cosine is outside.
Do you all agree or not?
I agree.
I agree, good job. I also agree, and it's also pretty visual in this case. 3x cubed is inside. So technically speaking, you see some kind of cosine of whatever is inside. I know how to differentiate cosine. What is the derivative of cosine? Negative sign of whatever is that thing inside. Remember that you don't touch it yet, you just copy it. You're not allowed to look inside. I also sometimes explain it as a computer games. You cannot go to the second level until you finish the first level, so that's why we don't differentiate right away everything. Times, and this is where chain rule starts. It says continue Do not stop because there's a chain reaction happens. There is a function inside of the cosine. Now you are allowed to see the function. The function is called 3x cubed. It's a polynomial. Derivative of 3x cubed is 9x squared. Amazing. So did you guys get it? That's all. Bless you. So copy over here, but then differentiate u prime. Okay, challenging example. Nah, people like that. What function is inside and what function is outside? So it is, let me read it just a second, 17 sine of x squared. Now go.
X squared is inside sine.
Yes.
Then sine x squared is inside sine.
Exactly. This is the perfect rational example. There is a function inside of the function inside of the function. That means you will do chain rule twice. This is u inside of sine, but sine is inside of sine. So if I want to draw a sketch, and I do like using Russian doll for sketches, the biggest Russian doll, that will be an ugly one, okay, ugly Russian doll. The biggest one is 17 sine. One step inside a Russian doll is sine. And then the inside, the small one, is x squared. X squared is the last one inside. And you always go from outside to inside, like you're unfolding the onion or the Russian doll. So let's do it slowly. Let's see what's gonna happen. First, I don't see anything inside. You have to think about this. I see 17 sine of something. 17 cosine of that something. Does that make sense? And you have to copy it because you're not allowed to touch it yet. So again, I will copy the whole thing because I'm not inside yet. So copy. See the trick? This is the complicated step that you cannot touch it right away. You have to have two products in this case because you do chain rule twice. Chain rule starts. Chain rule says, do not stop. Chain rule says, look inside. I see there's a function going on inside, some kind of processes, say inflammation inside of the skin tissues. And you're like, oh, the inflammation happens with the function as a function sine of something. Derivative of sine is cosine of that something. I have to copy it, you see? And every time you do differentiation, you have a product happening. One more product. Chain rule says, you know what, there's still something inside of inside. Now you can finally look and see x squared. And I'm differentiating x squared, and it gives me 2x, and I'm done. So this is chain rule inside of function, inside of the function, inside of the function, chain rule twice. This was chain rule twice. What do you think? Funny, but we do that right now in Calculus 3 class. We also do it in Calculus 2 class, and so on. And finally, let's do this one. Let's see which one is better. Higher orders, we have like 10 minutes. Perfect for... Would you like product rule or quotient rule?
Product.
Good choice. So product rule, quotient rule, and chain rule at the same time. You can imagine we can mix all of this exponential function with sine inside. How about that? So we can mix now everything for the test, and that's what we do. Okay, I see 4x squared minus 9 to the 6, and then minus 9x squared minus 4 to the 14. The first thing I notice is product. Product of two functions. How do we choose u and v, you asked? I see like a huge parenthesis like so. And I will choose this to be u and this to be v. And I will proceed, bless you, with the product rule. So it is a product rule. For now, I don't even see what's the problem. I don't see chain rule. It's a product rule. Let's do it. F prime is, the formula says, differentiate u. Bless you. And now when I'm trying to approach differentiation of u, I see that u is actually 4x squared minus 9 to the 6. So it is a polynomial raised to the 6th power. Thus, I have an inner function raised to the 6th power. I first differentiate the 6th power, right? Because this is the outside one. So it's going to be 6 goes down. This something to the 5. Do you all agree? What is that something? 4x squared minus 9. Chain rule says, don't stop. I see there's something inside. And you're like, yeah, I see that too. There is 4x minus 9 inside. Derivative of that 4x gives you 8x. And this is only u prime. This is only u prime. U prime required chain rule because u was an example of nesting functions. Now, what the formula says? Copy v, exactly. V is minus 9x squared minus 4 raised to the 14. That is your v. I just copied it. That is formula for the product rule. Plus, copy u. That is 4x squared minus 9 raised to the 6. That is u times differentiate v, and I again see that v is a polynomial raised to the 14th power this time. So it's going to be, I'm opening parentheses, 14 goes down, whatever is inside raised to the 13th power. What is that whatever? I have to copy it. Minus 9x squared minus 4. So let me repeat it again. Copy here, copy here. Outside derivative first, copy the inside part because you cannot touch it yet. Now chain rule says, please don't stop. I see there's a function inside. You're like, yeah, I noticed it before. I can see it's a polynomial minus 9x squared minus 4. Derivative of that is minus 18x minus 0. Make sure you have enough parentheses because this huge piece is v prime and this huge piece was u prime. So all this is v prime and you are done. No need to simplify. How about that? What do you think about that? And this is very, it has lots of implications. Imagine this is exactly what image processing is. So the animal are showing to the robot has tails. Next step, ears. Next step, 4 legs. Next step, black and white color. Next step, size 1 feet tall, and so on. So each step is changing, and that's why it's so useful. Question? Rest of the weekend, don't get sick, please. Be safe.